Okay, dear colleagues, you're welcome. Today, the speaker today, this is Jörg Koppitz from our institute. In the end of the year, usually we have a seminar or series of seminars when every person from the institute has to present a short account about the activity in the year. So this talk today by Jörg, this simply gives an account for some activity of him. Okay, this is not all the activity, but some activity. Jörg, please.
Thank you very much. A classical problem in semigroup theory, especially considering transformation semigroups, is to determine the ranks of a semigroup or to find presentations for semigroups. That we have done for a particular semigroup of order preserving transformations. And this is a joint work with a mathematician from Thailand, and the results will be published since the paper is accepted just yesterday. So, okay, let So let Xn finite chain from n elements, and Tn denotes the set of all transformation on the set. It means that our self-mappings from Xn to Xn, and this is called the matrix semigroup, and this is have the importance because it is an analogon to the Cayley's theorem. That means for each semigroup you can find a suitable set n such that this semigroup is isomorphic to a subsemigroup of Tn if we speak from finite set, and if we have an infinite set, then we have the same situation. That means each semigroup can be embedded in a transformation semigroup for a suitable set, and that's why it is important to study transformation semigroups. So, okay, a particular semigroup which is studied in the literature from many points of view is the semigroup of order-preserving transformations. Transformation, we have a chain, and the transformation is called order-preserving if it's preserved order. That means if x is smaller than y, then the same holds also for the images of this Gauss set. So, and as usually, we denote by On the set of all order-preserving transformations, which forms a submonoid of the symmetric semigroup Tn. Now we want to consider ranks and what for a semigroup. Let us any semigroup. So then the rank of a semigroup, or the rank of the semigroup, is the smallest size of a generating set of S. So, and this is the rank of a semigroup. And for example, the rank of the semigroup On is n. I have to say that is considered as a monoid. So it means in the generating set is every time the identity mapping included. Otherwise, if we consider it's not as monoid, the rank of On is n plus 1 because we have to add the identity mapping, which is the only permutation in this semigroup On. So now we want to recall the notation of a nilpotent semigroup. A nilpotent semigroup, we need a semigroup with 0, and an element S of a semigroup is called nilpotent if we have a natural number such that the n power of this element gives the 0. So, and by n of S, we denote the set of all nilpotent elements in S. Of course, it must not be each element in S nilpotent, but we call a semigroup nilpotent if we find a natural number m such that S M, that means all M products of S gives one element, namely the 0. So, and then a very useful observation is that if S is nilpotent, then it means all, it is exactly the case if all elements of S are nilpotent in our case. So, okay, now we want to consider a particular sub-semigroup of the semigroup of all ordered transformations. For this, we look a little bit in the history for some semigroups of transformations which are already considered. Namely, we consider the following set in the transformation, namely in an invariant. The set A of 1 up to n is called invariant if the image set of A lies in the same set A. So, and the transformation such that for a given set A, the image is every time in the set A. All this transformation together forms a semigroup, which was considered firstly almost more than 50 years ago by McGill Jr. This is denoted by Tn of A. Okay. If A is only one element set, then we can consider the set of fixed points, namely that fixed point of the transformation means as usually that the image is equal to the input. So that means x alpha is x, and such an element is a fixed point of a given transformation alpha. So, okay. And if we say, if we give a set A and ask that this set A belongs to the fixed point of alphas, then this forms a regular monoid, the set of all these transformations for a given A. Okay, I recall we give an A and ask for all transformations such that A belongs to the set of fixed points. It's not required is the set of fixed points, but belongs to the set of fixed points. And this was shown 10 years ago. This forms a regular monoid. So, and now we can ask, I said subset. Now what happens if we ask that the given set A is exactly the set of fixed points? So, okay, and this was also considered the semigroup already, especially for the case of order preserving transformations. Namely, we consider all order preserving transformations on the given set, such that exactly A is the set of fixed points. In the case that we have only a singleton set A, then we have a particular case, namely, then we have the set that ON in this semigroup is denoted by ON P, and is the set of all order preserving transformations such that exactly P is the fixed point. That means all other elements have image and input are different. So this is the set O and P. So, and this set gives a nilpotent semigroup. So that is not a big deal to show this, and this we have done also in this paper to show that this is a nilpotent semigroup. Another semigroup which is very well studied is the semigroup of order decreasing transformation. What is an order decreasing transformation? That means that the image is smaller or equal to the input for all elements from the set Xn. So, and such a semigroup is order decreasing, and this is usually denoted by Dn. That forms a monoid of all order decreasing transformation on n, x or xn. So, and now we consider the following semigroup. the intersection of all order-preserving transformations and the monoid of all order-decreasing transformations. So this monoid of order-decreasing transformations was very well studied, for example, by Uma. This is a scholar or a student, a previous student from the school in St. Andrew, by Ruskuch and Higgins, very important researchers in semigroup theory at the moment, and he was a student or a PhD student in this working group, and he has many papers about this semigroup Dn of all order decreasing transformations. Also considered this intersection with the order preserving transformations, and this is called Catalan monoid. So and this monoid have the name Catalan monoid because its cardinality is the Catalan number. So this example shows that the intersection of two important semigroups of transformations gives an interesting monoid of transformations, which is well studied because this have particular properties. I want to only recall that the cardinal number, Catalan number of C0 is 1, because here we have only natural numbers, and then I want to add this. And so what we can recognize. Our semigroup ON1, that means all order-preserving transformation where it's 1 the only fixed point. This is the first one, this is ON1. Order-preserving, 1 is the only fixed point, is the maximal nilpotent subsemigroup of the Catalan semigroup for N. So, okay, this is a important observation. And 10 years ago, a Turkish mathematician in a group have determined the cardinality of the semigroup O and P. It is the product of this both Catalan numbers Cp minus 1 and Cn minus P. Okay, and this semigroup O and P, that means all order-preserving transformation. P is the only fixed point, have the following characterization. It is not hard to see, but it is very useful to notice the elements which are smaller than P-sint have an image which are greater than the input, proper greater, and the elements which are greater than the fixed point have a proper smaller image than the input. So, okay. In particular, we have the situation that the element left and right from the fixed point have the same image than the fixed point, namely P. It is the only possibility in the semigroup for the Nebiers of the fixed point. So let us consider an example. We put P as 5 and N is 8. So then we have the following transformation semigroup. So 5 is the fixed point. Then we look, no other element is fixed point. And you see the observation, left and right side from the fixed point have the same image, namely the fixed point 5. So this is a general construction fixed point, and then you have here such like this T of the head, so from this elements. Okay, this is no element in our semigroup, almost the same, but look, here is the difference. Here you see this semigroup second fixed set point. And so it belongs not more to O and 5, because I recall 5 is the only fixed point in this semigroup. So only to see which kind of transformations we are looking, and now I want to recall an important result about the rank. The rank was the size of the minimal generating set, and the size of a minimal generating set of O and 1 is this product. This is a result from 2 years ago from Yakci, a Turkish mathematician. And it is easy to see both transformations are isomorphic. What this means, you can think this should be the case, because here is 1 the only fixed point, and here is only n the only fixed point, and by symmetry you can assume this should be isomorphic. That means only mapped 1 to n and n to 1, and in this way you have the isomorphism. More interesting is that we have the following isomorphism, namely ON2 is isomorphic to ON minus 1, 1. So that means you see here is an ON, and here we change to other set of transformation. Here we have n elements, and you have an n minus 1 element set. Here, but here you have fixed point 2, and here you have fixed point 1. And this is a result which was also motivated by reviewer of our paper, and we add this interesting result to our research. And now appears the question: can we do this also for 3? And then we have maybe here n minus 2. The answer is no, because this is a special case, because if you have here 3, then the elements left side from 3 from the fixed point 3 have not all the same image, and this is the main point, that you can make such a consideration, that in 2 the image of 1 and 2 is the same. If you have here 3, the image of 1, 2, and 3 have not more be the same, and that's why you have not more such a isomorphism in general. So now we consider all elements in O and P which are irreducible. That means you cannot show it as a product of other 2 elements, and we could show that, or we could characterize this set in the following way. They have this transformation have the following property. They have at least one element which have only difference 1 to between image and input. That means here you have the difference between image and input is 1, and you find exactly 1, except of the neighbors of P, because the neighbors of P have the image P. That means they have exactly this property, that the difference between image and input are 1, but we need exactly 1 additional element, which is not a neighbor of the fixed point, and all these transformations are irreducible. That means all these transformations in O and P cannot be represented as a product of 2 other transformations in the semigroup. So, okay, let's see an example what I mean. Fixed point was 5, and here you see 1 has difference between 1 and 2 is exactly 1, and here we must exclude it here, because as I mentioned already, this is every time 1, then this would be not a requirement. So that means we have additional one element in the domain which have difference 1 between input and image. So, so I recall this the semigroup ONP is a nilpotent semigroup, and because it's nilpotent semigroup, we can use the following result, that the rank of this semigroup is exactly the cardinality of the set of all irreducible elements in the semigroup. And this is nothing else than the cardinality of the semigroup minus the cardinality of the elements which are which are products of at least two elements. So, okay, and we know that the cardinality of this of the set is exactly the same, or we could show that this the cardinality of this set is exactly the cardinality of the semigroup. That means we go to another set, namely to the set xn minus 2. That means we have a chain which has two elements less, and consider as a fixed point p minus 1. So, and then this cardinality is known, and then we know also this cardinality. So, and then we could show that the rank of ONP is exactly the difference between these both products of Catalan numbers. So that was the first main result of our published research. So, and the next one, we want to go to what I mentioned, presentations. It is well known that presentations are very important. For example, in group theory, we know the presentations for several groups, and now it's also studied the presentations for transformation semigroups. There are several transformation semigroups which are the presentations are known. Very important in this working is Vitor Fernandes from Portugal, as well as James East from Australian, and also Nick Rutschkuch, which have written his PhD thesis about the presentations from transformation semigroups. So, okay. So now we want to find for a presentation for the case n is p is 1. So that means not for all p we could not find such a result, but for p is 1 we could find a presentation for the semigroup. So at first let us recall what is the semigroup presentation. At first we need a set y, and then we make the free semigroup over the set, and we consider a relation R on the free semigroup. So then we have any relation, and from this relation we can generate in the usual way the concurrence. That means we make the closure from this relation and obtain the concurrence, which is generated by the relation of R, which we denote by R sharp. So, and if there is an epimorphism from the free semigroup on our set Y to a given semigroup S with the property that R sharp is the kernel of this epimorphism, then we say S has semigroup presentation Y R. In this case, we denote R are the generators. In fact, to find the presentation, it is very helpful, or it is more than necessary, to know generators of this the semigroup, and R are the relations. Of course, such a presentation you can find everywhere. You can take all elements as the generators and make all relations, and then you have a presentation. The question is to find a good presentation. That means with a small number of generators and a small numbers of relations. That means in the set of relations should be cards in such relations which are not necessary to find our chart. That means to find the set R such that we can not reduce any relation from the set R such that we get the same congruence. So, and this is the aim, to find such a relation. Let's see first the presentation for semigroup. So generators as a semigroup. I speak not as a group presentation. In a group presentation, that is different. We have a semigroup presentation, and the semigroup presentation for the integer by plus have the generators minus and plus, and then you have these three relations. That means I make here a mistake. That is here is a plus, not minus, and then here you have here is this is exactly conversely. This both must be conversely. Here's +1 and here's -1, and then you have here this community. So if you have this one, then you have a semigroup presentation. But here with this mistake, this must be +1 and this must be -1. Okay. So okay. Okay. So okay. So then I want to give some technical to find this semigroup presentation. Namely, let we consider the following set of mappings from the set xn in the set 0 up to n-1 with the following properties. Oh, so we consider all mappings from xn in this set 0 until n-1 with 1 goes to 0, this is fixed, and all other images are greater or equal 1. And we have at least one element in this in xn which have as image 1, but it is not the 2, not 2. It means from 3 up to n we find an element which the image of G is 1. And then we have additional that the image of x plus 1 is smaller or equal xg plus 1. That means the right neighbor of x have an image which is at most 1 greater than the image of it himself. So, and all this transformation we consider, and the set of all these not transformations or of these mappings, it's not a transformation, all these mappings we consider and denoted by an. In order to get an alphabet, or we want to distinguish between mapping and variable, and we do this in the following way. Maybe sometimes it's not necessary to do this, but I want to do this here, that we speak really from variables. Namely, I give each x the index of an. It means this set belongs of all x indexed with elements of an indexed with mappings. So, and we can calculate this. This set Y have the same cardinality of the set an. So, and moreover, we could prove this set an is exactly the cardinality of this set n is exactly the cardinality of this set of irreducible elements in On. It means we could find such a one-to-one mapping between this set and this set. And from this set, the cardinality is known. I already mentioned this one. And so that means we know the cardinality of the set of variables. It is the difference of the both Catalan numbers, Cn-1 and Cn-2. So that means this should be our set of variables. Now we are looking for the set of relations. So at first we point out one particular element in An, namely this element which has one, which is a constant mapping, namely the constant mapping with the image 1. Not really constant, because constant from 1 to upon 2 to n, because we know that the image of 1 is 0. That means you have 1 is 0 and the rest is image is 1. This mapping in An is denoted by omega. So, okay. So, and now we want to define for each element in An a new element G hat in the following way. For x is 1, we keep the image. For x is 2, the image is 1. And for in otherwise, we define this in this way. What is f? F is the following mapping. This is 1. If the image is here inside is 0, then this gives 1. And otherwise, the image of f is every time the input. Only if we have here inside, if inside you get 0, then f maps to 1. Otherwise, this mapping f maps to the maps identical. So, okay, this is written here. So, okay, now we go over to our set of relations. So, the set of relations are, we consider two sets of relations, namely the following. We have any element in An, and this multiplied with the square of W. This gives Gn multiplied with W. You see what happens here? The square of W reduced to only W, but this G comes to this new G hat. So that means in each case, this relation have to reduce the numbers of variables in a what. So, and the second kind of relations do the following. If you have any two elements in An and you multiply this, then you get a new transformation multiplied with W. What is this plus? This plus is defined in the following way. So, and this is, if it's 1 is a 0, if it's 2 is x, if the input is 2, then we have 1. And otherwise, we calculate the following. We make the difference from x and xg, this means from the first one, and then we map this by the second one, and this minus the element for the first one and minus 1. We can show this is well defined. This gives again an element in An that we have checked. This is the case, and now we understand here this this relation do the following. You have here two products, and this reduced one product with and together with omega. That means if you have in your head a sequence of products, then you can see that you can reduce it to the following, to 1 in G and a power of W alpha. And then you can reduce it, the square, to only 1. But here changed, of course, the first input element. It means using these relations, we can reduce any word to a 2-element word. This is the idea of these relations. So, and we can, it is not hard to see, both relations are distinct, because you see here, this is clear because you can see here I have a square in W, and here you have 3 elements, and here you have never 3 elements, and so that means no relation can appear double. So, and now we want to ask, because we want to know how many relations we have. So, and then we have to, we can find the following. This is nothing else of this because they have no joint, no common element. We have to add this the number of these relations and the number of these relations, and then we can use the knowledge about the cardinality of AN, what I showed before, and then by some calculations we get this one is the cardinality of the set of relations R1 union R2, and it is the product of this both sums of or differences of Catalan numbers. So, okay. Now we go back from AN to a transformation. That means to each of this element AN, we can define a transformation in O1, namely that we map the following: X map to X minus G of X. What this means? It means nothing else that the image of X is nothing else than the difference between X and the image of X in the transformation. So that means this G is represented the difference between X and between the elements and the images, the difference. This is represented, and then we get such a sequence of differences, and the sequence of differences between image and input is exactly this transformation G. Then G can also considered as a sequence of n elements. So in order to find a presentation, we need an epimorphism. So, and how we define this? So input must be a variable, and output is a transformation. It is this epimorphism is defined of y plus. That means of the free semigroup of y, and of course, if you look for the generators, it's enough to define this for the generators, and then this extend automatically to the free generated monoid. So that means we have only defined this mapping for the generators for the of this free semigroup, and I want to point out that we have really a semigroup, not monoid, because the identity mapping belongs not to the semigroup ON1, because we have only one fixed point, and the identity mapping have, of course, n fixed point, namely all are fixed point. So that means we have this is not monoid, this is semigroup without identity element. So, okay, so then we define this. Here you have this variable xg, and this maps to the transformation ag. So, and this is, we have shown this mapping is well defined. It means this ag is seriously an element in ON1 that have check it. So, and in this way we have defined this one, and we could prove that the kernel of this mapping is exactly the congruence generated by R1 and R2. I have to say there are different methods to find presentations. In papers of Fernandez are given two methods to find presentations. What I use here is a method which I found in papers by East. In here, he also show exactly this kernel. The kernel of a epimorphism is this is the congruence generated by the given relation, and I have to say, the other techniques are only consequences, equivalent consequences of this method. And sometimes they are quite useful, but we pointed out that in our case, we could show this here in this way, not so complicated. And then we could find our second main result of our work, namely that ON1 has the semigroup presentation Wn. This is this set what we found is W. This N is not necessary here. This is only W, not Wn, and set of relations. So we know how many elements we have in Y. And we know how many elements are in R, and this gives us presentation for our semigroup ON1. So let us consider this an example, namely we put n is 4. So in the case n is 4. So then we consider the semigroup O for 1. That means what we consider? We consider all transformations on the set 1, 2, 3, 4 with the property order preserving plus 1 is the only fixed point. So, and then we can easily check that we have exactly 5 such transformations. Namely, so we must look here. 1 is every time fixed point. So then we have order and the only fixed point. So then we know already that the Navier, that means 2, have also the same image than the fixed point. That means here this both must be 1. So this is fixed. So now we can distribute the rest. It must be order preserving, and no can be fixed point. So what is possible for 3? So for 3 we take 1. What is possible? What we can do if we have here 1, then order preserving, and we can here put 3. And we could put 2 here. 4 is not possible, because if we put here 4, then we have 2 fixed points, but 1 is the only fixed point. So this is the only possibility for 1. So then we can put 2. So what can and 1? Yeah, I forgot to. 1, 2, 3. So this is the 1, 2, 3 is possible if we have 3 as 1. Now we can put here 2. What is possible? Order preserving, we have 2, 3, and 4. 2 is possible, 3 is possible, 4 is not possible, because this would be if a fixed point, although only this both. Can I put here 3? No, 3 I cannot put here, because 3 would be fixed point. Can I put 4? No, 4 is not possible, because we know that by that, or we can say also already now we can say 2 is the highest one. What we can do, because the image is by the result of Ike at least it's really proper smaller than the input, because we are right side of the input, also greater than the input, and then the result of Ike said, then the image of the input is at proper smaller than the input. So that means for 3 we have only the possibility 1 and 2. So we are sure that these are all elements in ON1. So then we can look what is omega. Omega, T omega is related to this one here. You see here is the difference 0, and the rest here the difference is 1, and this gives us this C is related to omega. So, and then we can see now we can we now take the transformations as the variables. And not in the theorem I have denoted especially by variables with index, but now we can consider the transformation itself as the variables. So then we have A, B, and C are the generators. These are the generators, this 3 one, because they have here an element which have differences 1. We have here differences 1, here differences 1, here differences 1. This was the property to be in AN, that the difference is here 1. And here you see never is a difference 1, never difference 1, not difference 1, not difference 1. So this was, these 3 elements are the generators. So these elements cannot, and we know this, these elements can generate it by the other elements that we have shown. So, and if we take the relations R1 and R2, then we get exactly these relations for our presentation. So this is a presentation of O for 1, and in this way we can find for every n the presentations for O n1, and this was the results which we have found together in research in joint research with the scientific from Thailand, and this is what I want to present today. Thank you very much.
Okay, let's thank the speaker for the nice talk. Do you have any questions? You can simply ask. If no questions, can take the speaker once again.
Thank you.
The next you have another talk, you have the information in time.
Академик Дренски, не се чува добре нещо от вашия компютър.
The other talks. Okay.
Okay, I will stop recording now, and I will transfer the hosting to Jörg, because the rest of the meeting can be used as an informal conversation with the speaker. I think this is the normal thing to do. So I stop recording now.
The next Friday. Я ще ви оставя всички. Окей, чао.
Виждане и от мен.